Okay, now one parallel RLC circuit is given where current source is connected. Again, this current source is active from t is equal to 0, and also the initially the inductor or capacitor is not having any initial energy. Okay, but the source is applied. Okay, so whenever you have a parallel circuit, okay, whenever you have a parallel circuit, there are three varieties of solutions are possible. Okay, if it is a parallel circuit, alpha is 1 by 2 RC and omega naught is equal to 1 by square root of LC. Then 2 into R value is 1 by 2 to 1. Then finally alpha is 1. Then what is omega naught? 1 into 1 and finally 1. Okay, so that means what, both alpha and omega naught is same. When this is same, when alpha and omega naught are same, then this will provide critical damping. Okay, critical damping. Okay, critical damping means what is the, again, the roots will be equal. Okay, and also they are negative and real. Okay, so once if it is critical damping, what is the solution? Okay, the solution will be like e power minus alpha t a1t plus a2. Okay, this is the solution. Okay, whenever you have a critical damping, again this a1 and a2 may be non-zero, or any one of the quantity may be zero. Okay, so finally the response will be in the structure. Okay, so what I'm telling, finally a1 may be zero. Once if a1 is zero, you'll get a2 into e power minus alpha t. If a2 is zero, then you'll get t into e power minus alpha t. Okay, now we'll see. So then what is the Laplace transform representation here? And also please note down here, V means the voltage, the instantaneous voltage across the capacitor. That means that voltage is same as what is the voltage across other element, that is inductor or resistors or even the current source. Okay, but this current source is active from t is equal to 0. Before t is equal to 0, the current source is not there. Exactly from t is equal to 0, this current source will be applied. That is the concept of ut, because ut will be active only when t is positive, that is from when t is from 0 to infinite. Okay, so the capacitor or inductor is not having any initial energy. Then once if it is not having any initial energy, then how to represent that? First, the current source. Okay, if you take the Laplace transform, then that is 2 by s. Laplace transform of u of t is 1 by s. And again this is resistance, remains as resistance. Then SL. Okay, for inductor it is SL. Okay, simply S. Okay, for capacitor 1 by SC. Okay, so it remains as 1 by S. And again this voltage, we'll call it as once if you take Laplace transform, that is V of S, that is V of S. So now you can apply the KCL at this node. Okay, all these nodes are same node, so all are same point only. Okay, so all are same point, so you can apply the KVL at this node. Okay, so sum of the current leaving from the junction is equal to 0. So what is the current leaving in this branch? That is 2 by s. What is the current leaving here? Okay, the voltage, the nodal voltage. What is the nodal voltage of this node? Okay, the nodal voltage of this node is Vs only, because with respect to this point voltage is Vs, then with respect to this point also the voltage will be Vs. Okay, the Vs is the nodal voltage. Okay, so minus 2 by s, and then Vs divided by 1 by 2 plus V of s divided by s, V of s divided by 1 by s is equal to 0. Then you make the mathematical arrangement, then you'll get finally V of s 2 divided by s square, s square plus 2s plus 1. Finally you'll get this. Okay, then once if you modify this, 2 divided by s plus 1 whole square, 2 divided by s plus 1 whole square. So again here you have to take the inverse Laplace transform. Okay, here we have to apply two formulas. One is, say for example, if Laplace transform of t is there, then we'll write 1 by s square. If Laplace transform of e power minus at is there, then we'll write 1 by s plus a, 1 by s plus a. But here we are having s plus a whole square. That means again t also will be there, e power minus at also will be there. Then once if you take the inverse Laplace transform, anyway, and again Laplace transform of t is equal to 1 by s square only. So you can take 2, okay, separately. Then this is t multiplied by e power minus t is the solution. Okay, so you try the same example with the time domain technique. Okay, with the time domain technique. Okay, so already we have seen. So you'll get in this format. Then you supply the initial condition. Okay, what is the initial condition given in this problem? Okay, the initial condition here is it's like this. Say initial condition is the voltage across the capacitor is 0. They are not given the any voltage, and also the current through inductor. Okay, current through inductor also 0. So with this initial condition, you try to find out what is A1 and A2. Then try to get this answer. Okay, now we'll see the another problem. Find IT 200 microfarad 1 by 2 Henry I 2.5 ohm. At t is equal to 0, we are opening the switch. Okay, this is 5-volt source. Okay, at t is equal to 0, we are opening the switch. That means what? Just before opening the switch, what is the state of the circuit that we have to identify? Okay, so before opening the switch at t is equal to 0 minus, circuit will be in steady state. Okay, before opening the switch. Then once if it is in steady state, okay, then see the circuit would have been like this. Okay, this is open. Again, this is short. Now this is 5 volt, 2.5 ohm. Once if this is the case, then what is the current through inductor? The current through inductor IL is 5 divided by 2.5, that is 2 ampere. Definitely this is short circuit. Then what is the voltage across the capacitor? Vc of 0 is equal to 0. Voltage across the capacitor is 0 because this is short circuit. So then what is the initial condition? IL of 0 minus is equal to 2 ampere. What is the capacitor voltage, initial voltage, that is 0 volt. Okay, so this is the initial condition. Now we are applying the switch at t is equal to 0. So again, the current across the inductor cannot change suddenly. Then you will get IL of 0 plus or IL of 0 as 2 ampere only. Similarly, voltage across the capacitor VC of 0 plus or VC of 0 is equal to 0 volt. Now the capacitor, now the capacitor is having no initial voltage. Okay, then once if it is not having any initial voltage, then simply we can represent the capacitor with 1 by SC. That means what? The capacitor is not having any initial voltage. It is simply capacitor only. Even okay, that at the time of switching, the capacitor is not having any initial voltage. So I can replace the capacitor with the 1 by SC. Okay, SC. Then I can substitute what is C value. Okay, 200 microfarad. I can substitute that. Then how to replace the inductor? But the inductor is having some initial current. Okay, so inductor is like this, but it is having some initial current I naught. Okay, so whenever the inductor is having some initial current, then how to represent? Minus plus, okay, Li naught minus plus Li naught. Then simply the inductor will represent here SL. Okay, once if the inductor is having initial current, then we'll represent like this. Then what is the value of L into I naught? Okay, L value is 1 by 2. I naught value is 2, okay, I naught is the initial current through inductor, then L I naught value is 1. Okay, again L we can substitute, okay, then S by 2 you will get, okay, once if it is SL, then instead of L we will substitute 1 by 2, then S by 2 we will get, okay. So then just after the switching, okay, you see at the time of switching what you are doing, you are opening the switch, okay. Once if you open the switch, what will be the state of the circuit? You are disconnecting the source from this network, okay. So what is the state of the circuit after t is equal to 0? Okay, after t is equal to 0. So after t is equal to 0, what is the state of the circuit? You are opening the switch. Once if you open the switch, the voltage source will be disconnected, okay, voltage source will be disconnected. Then you will get a network like this, 2.5 ohm and 1 by 1 by SC, okay. Then this is minus plus 1, this is SL, okay. Now this is the state of the circuit after opening the switch. But now what we have to calculate, we have to calculate what is the current through this inductor. That current in the Laplace transform domain, we'll call it as IS, okay. Now we have to calculate what is IS now, okay. So once if you want to know this IS, then what we can do, because this is open, once if this is open, what is the current here? Current to flowing here is 0 ampere, because this side is open. Then how to find out IS, okay. Then you apply KVL in this loop, you apply KVL in this loop, okay. You go in this way, you apply KVL, then minus 1, okay, plus SL into IS. Okay, so because whatever the current that is coming this way, the same current has to come this way. And again, the current, because here it is 0 ampere, okay, then here also it will be like 0 ampere only. So 1 0 ampere plus IS, then here it will be like IS, okay. Then minus 1 plus SL IS, then IS into 1 by SC, okay. So IS into 1 by SC is equal to 0. Then you make the adjustment, IS SL plus 1 by SC is equal to 1. IS is equal to S square LC plus 1 divided by SC. Okay, because I am not substituted these values, C values, because it is a little bit tricky value. That's why I will substitute later. Finally, I will substitute what is this value. Okay, even you can substitute here itself, but somewhat it will be confusing. That's why I'll substitute in the final step. Okay, then we need IS. Okay, we need IS. Then IS is equal to SC divided by S square LC plus 1. Okay, SC, you take that LC outside, then S square 1 by LC. Okay, C cancel. C cancel, then you are getting 1 by L. What is the value of L? L means 1 by 2. Okay, then you'll get 2S divided by S square plus 1 by LC. Okay, just you calculate what is LC. That you calculate what is 1 by LC. L means 1 by 2. What is C? C value is 200 microfarad. Okay, 200 microfarad. 200 microfarad. Instead of writing micro here, I can write 1000 K here. I can, instead of writing micro here in the numerator, I can write 1000 K. Then this 200 cancel. Then how much I will get? 100 cancel. Then I will get 10K. That is 10 power 4. Okay, so this is 10 power 4. Now the I of S value is 2S divided by S square 10 power 4. That I can write like 10 square. Okay, now if you see, this is like 2 into S divided by S square plus 10 square, because we are having one formula, Laplace transform of cos omega t is equal to S divided by S square plus omega square. So with that formula, if you take inverse Laplace transform, I of t will be 2 sine, 2 cos, because it is cos, and then omega value is I think omega value, we made a mistake. Not, it is not 10 square. 10 power 4 means 100 square. 100 square, 100 square, then 2 cos 100t is the answer. Okay, so whenever you write the equation, you just put this value, okay, with this u of t also, okay, to indicate that this is valid from t is equal to 0 to infinite. Okay, 2 cos 100t, this is valid from t 0 to infinite. This is the solution. Okay, the same thing you try to do it by the time domain method. Okay, the same question you can do it with the time domain method also. Okay, so next we'll see the another problem. Find complete expression for P. 1/4 Faraday. 5 ohm, 1 Henry, and then switch is opened at t is equal to 0. Okay, then this is 24 volt. Okay, if you see this circuit, this is like a series RLC circuit, because once if you open the switch, okay, once if you open the switch, this is something similar to series RLC circuit. But before opening the switch, okay, the before opening the switch also, the source is connected with this. Then again, it will be having some initial voltage. Okay, it will be having some initial voltage, and also the inductor also will have some initial current. Okay, so this is the series RLC network with the initial current and also with the initial voltage, with the initial current and also with the initial voltage. In general, for a series RLC circuit, if we do not have this one, okay, once if you have a switch here, okay, we will have energy either in the inductor or capacitor. That too, definitely you will have a energy only in the because if it is open, then you will have a energy only in the capacitor if you are having the switch here. But once if you are having this circuit format, then there is a possibility that you may have a energy both in the capacitor as well as in the inductor. Then once if you have a RLC circuit, you know what could be the response. Okay, so now the capacitor, both capacitor and inductor is having initial energy. That's okay. Then after opening the switch, what is the state of the circuit? After opening the circuit, this is like series RLC with the value R is equal to 5 ohm, L is equal to 1 Henry, and C is equal to 1/4 Faraday. Okay, this is the state of the circuit after opening the switch. Then if it is series RLC, what is alpha? Okay, if it is series RLC, what is alpha? Alpha value is um, R by 2L. R by 2L. What is omega? Omega is 1 by square root of LC. Okay, 5 by 2. Okay, then what is omega? Omega is 1/4. Okay, then sir, what is the answer? This is 2. Okay, now alpha is 5 by 2. Okay, then this is like 2.5. Okay, 2.5. So alpha is greater than omega. If alpha is greater than omega, what is the solution? Critical damping, under damping, or over damping? Anybody?
Over
Overdamping, sir.
Over damping. Okay, once if it is over damping, what is the response format? Okay, if it is over damping, then you will get the roots which are real and also not equal. Okay, that will be on the negative axis, okay, real but not equal. Once if it is not equal, then you will have this format e power minus say for example again if root value is again s1t, again the s1 will be negative, okay, a e power s1t a1, then a2 e power s2t. But along with this you will have some initial condition, because this again this is a network, this is not a free network, this network is having some source, okay. Even after applying the switch, the network consists of the some source, okay. So this is the network with the source. Once if you have a network with the source, then definitely you will have some initial voltage, some initial voltage. That too, if you see this is like series RLC format, then finally this voltage will be like 24 only, because again from the basics, you know, once if you have a series RLC circuit, okay, then if it is a circuit with the source, then what will be the final equation? These are all, these two are like transient response, okay. These two is like a transient response, this 24 is like steady state response, okay. Because irrespective of the operation of the switch, the moment you open the switch, after a long time, what will happen, whatever the voltage that is available here, that voltage will appear across the capacitor, because at steady state the capacitor will act as a open circuit. Irrespective of the initial voltage, the final voltage across the capacitor will be the same as the what is the source voltage, okay, that will be 24 volt. So once if you measure what is the voltage across the capacitor, okay, here the V means the voltage across the capacitor, okay, here the V means the voltage across the capacitor, okay. So the voltage across the capacitor will be finally 24 volt, irrespective of what is the initial voltage here. So finally your answer will be something like this, okay. So but we'll not go by ordinary method. Now we'll apply the Laplace transform method, okay, then we'll try to get the answer, okay. Now first we have to find out what is the initial voltage, what is the initial current across the capacitor as well as the inductor, okay. Before opening the switch, what is the state of the network, okay. The network state will be like this, say this is 5, and again inductor means short, capacitor means open. Again before opening the switch is closed, okay. This is switch position, switch is closed, and this is 1 ohm, 1 ohm, this is 5 ohm, okay. So this is at t is equal to 0 minus, okay. At t is equal to 0 minus, circuit will be in steady state, okay. Then now you are having 24 volt, this is 5 ohm, this is 1 ohm, okay. Now what is the voltage, this voltage, if you see the voltage here is same as what is the voltage across 1 ohm, okay. Then voltage across 1 ohm, for that you can apply the voltage division rule, okay. So VC is equal to 24 into 1 divided by 6, that is 4 volt, okay. 4 volt is the voltage across the capacitor. Then what is the current here, that is IL, okay. Current IL is same as the total current in the network, that is IL is equal to 24 divided by 6, that also 4 ampere. Now this is the voltage VC0 minus, that is same as VC0 plus, that is same as VC0, that is 4 volt, and IL0 minus, IL0 plus, IL0 is 4 ampere. Now both the capacitor and inductor is having some initial energy, okay. First for a capacitor, okay, if the capacitor is having some initial energy, say for example this is capacitor and it is having some initial energy, that energy I will mention like V naught, okay, initial energy with V naught. Then how to represent the capacitor with initial energy, okay, I will replace this with the separate voltage V naught, I will replace this with the separate voltage V naught, and I will write the capacitor separately, okay. Now you apply the Laplace transform. Once if you apply the Laplace transform for this one, then this is V naught by S, then this is 1 by SC, okay. So 1 by SC, okay. Now you know what is V naught, V naught value is simply 4. Similarly for inductor, okay, so inductor is having initial current, that is I naught, and this is L. Again directly in Laplace transform domain, this is minus plus, Li naught. Okay, this is directly in the Laplace transform domain. Okay, so this is SL. Okay, don't put 1 by S here. Okay, this is Li naught and this is SL. Okay, so now you can replace the capacitor. Okay, after switching, you can replace the capacitor network with this. Okay, and then inductor with this combination. Once if you replace, okay, with this combination, and also note down, after switching, this 1 ohm will not be there because that 1 ohm will be removed. Okay, after switching, because you are opening the switch, then this 1 ohm is like it will be removed. Okay, then after opening the switch, what will be the state of the network? That the state of the network after t greater than 0, okay, will be like this. This is 5 ohm. Then you replace the inductor. The inductor is present here. You replace the inductor with this value Li naught. Yes, L. Okay, again, what is the value of L means 1 Henry. What is I naught? 4. Okay, so I'll get 4 here. Okay, so minus plus 4. And also uh, what is the SL value? Okay, simply yes, because L value is 1. Okay, similarly, you replace the capacitor here. Capacitor initial voltage, again 4 by S. Okay, and then what is the capacitor value? Capacitor value is 1 by 4. Okay, capacitor value is 1 by 4. Then you apply that 1 by SC. Okay, 1 by S4, then 4 by S. Okay, so this value also 4 by S. Now anyway, the resistance that was present here is open, but now we are interested in what is the voltage across the capacitor. Okay, see, if you see, this is the equivalent representation of the capacitor. Now we are interested in what is the voltage across the capacitor. That we will write V of S, that means voltage across the capacitor. Okay, now again, the source is there. What is the source? 24 volt. You apply the Laplace transform here because you are considering the circuit from t is equal to 0. Okay, then that means after switching, you are considering this network, then 24 divided by S. Okay, here you will get 24 divided by S. For a source, you take a Laplace transform, then this is 24 by S. Okay, then you do something, then finally you can find out what is Vs. Okay, so one thing, you can find out what is the current here, because this loop consists of some voltage here, some voltage here, some voltage here. This is the voltage, then and also resistance. Okay, 5 ohm, yes, 4 by S. These are all the resistance. Then this network consists of only voltage and resistance. Then you can find out what is the current here. Okay, you can find out what is the current here. Then what is the voltage here? Okay, once if you calculate what is I of S, then the voltage here is, okay, 4 by S plus 4 by S into I of S is the answer. 4 by S plus 4 by S into I of S. You just try it out. Okay, now I will do by some other method. Okay, just try to get this. Okay, so see, when you measure the voltage here, the voltage here is same as what is the voltage here plus what is the voltage here. So definitely this is 4 by S. But what is the voltage here really depends on what is the overall voltage in the network, what is the overall resistance in the network. That means you have to apply the voltage division principle for this 4 by S alone. Okay, then what is the overall source in the loop? That is 24 by S plus 4. Again, if you see, if you take this as a 24 by S and again 4 will be like a addition. Okay, minus plus minus plus, but after plus again you are getting plus. That's why here minus. Okay, 4 by S. This is the total voltage source in the network. But I am interested what is the voltage here. That means that term I will write it in the numerator. Okay, I need what is the voltage across 4 by S. Then I'll write the total resistance in the network, that is 5 plus S plus 4 by S. Okay, then you do the arrangement here. Okay, once if you do the arrangement, okay, okay, you can do the arrangement. Later you will get V of S is equal to 4S square 30S plus 96 divided by s into s plus 1 and s plus 4. Okay, then you apply the partial fraction technique. Okay, a by s and b by s plus 1 and then c by s plus s plus 4. Okay, you apply that this technique, then finally you will get 24 divided by s. Okay, then minus 64 by 3 into s plus 1 and then 4 by 3 s plus 4. Okay, then if you take inverse Laplace transform, this will be 24 minus 64 by 3 e power minus 64 by 3 e power minus t e power minus t and then plus 4 by 4 by 3, this is 4 by 3 e power minus 4t. Finally you have to put u of t. Okay, so this is the final answer. Okay, just you compare with the um, original one. See, uh, uh, okay, so we need finally the answer would be in this format 24 plus something a1 e power s1t a2 e power s1t. So we got that format finally, that is 24 where a1 value is negative, the other value is positive, and then one root is 1 minus 1, the another root is minus 4. Okay, so the same question you try to solve it with the ordinary time domain technique and try to get this answer. Okay, so with this I will stop. We'll see the remaining things on tomorrow. Okay. Um,